King. Price. Rounsley. Spore. Stanek. Hall. Green. I got that one. Alvarez. Rapoli. And Sergeant Keenan. Alright, as you can see, we'll be going over the signal flow today. Looking at the transmit path, the receive path, the standby loopback, and Orderwire. So let's take a look at these. The first thing I'm going to bring up is yesterday we went through the branch assembly, so I researched a little bit more. This is coming off of I think it's a tech website. I'm trying to remember the name. But it showed pictures, and I thought this was really a good idea of presenting it to you to let you know, hey, we're not lying here. So this is passive. What does a passive mean? It means there is no electricity that powers it up. It is either a 3 or 4 port device. In our case, it's going to be a 3 port. You can imagine that positions 3 and 1 are either transmit or receive, and 2 is where the antenna is either going to receive the transmission or transmit out the baseband signal. So, excuse me, RF with the baseband. So you have, in our case, the 3, let's just pretend it's transmit. It will not go on the 1 line. It will not get in there. It's just the way the nature of this particular device is and the way they've got it set up. It just knows it using, and from what I've gathered, from what I've read on it, it uses the impedance value of the transmission. So as you well know, frequency does play a part in how the impedance works. Remember, we want the antenna electrically long or electrically short depending on the wavelength. So with the frequencies involved, since they're 200 megahertz apart, it's able to sense the impedance on there in which way it needs to go. Next up, we have a couple different examples of duplexers. Again, this is these devices that take a look at what's going, in our case was a forward and reflected power. You can see that there is one place to take the output at. We have a diplexer. Now this one is where we combine 2 signals, put it on 1 wire and send it back and forth. That's what your 2-foot or 150-foot cable does. And if you take a look at the connectors, you will notice that there is 1 coax cable in it. It's pretty small, very flexible, but there's only 1 coax cable. Everything else is power, and I think some audio signals are on there for Orderwire. When you have Intercom and Orderwire on there. Had to think about it a second. So those are some items that we have out in the field and that is in the TISR to give you a better sense of what's happening. So let's take a look at the baseband assembly, and what we are going to look at is the signal flow on the diagram portions, your electronic diagrams. So if you either want to follow through with the slideshow or follow through the diagrams and make your notes on it, that would be a good thing. And again, we're going through the tech order with this one, starting with the transmit. Now there is a sequence of switches and what it has to be. When we are talking transmit on our TISR Jerk 239, we have it in the operate position. That means you're transmitting. Operate switch is in the baseband assembly, and if you take a look, let me see if I can blow this thing up here. if you take a look at the underneath the test tone and above the meter switch, you will see where it says standby and operate. This is assuming that we are having this switch in the operate position. When you start to put everything together, it is important for you, and it even states it in the TO, that you have to make sure that that standby operate switch before you power it on is in the standby position. Standby is also another name for loopback. But in our case, when we are going through the schematics here, or C's and D's, we are looking at this particular switch in the operate position. In other words, we're transmitting. So the first place we're going to go to, this is page 4. Hang on just a second. C's and D's. Make sure I got this right. Ah, yes. If you got the paper copy, the large one, this is page 4 on your C's and D's. Had to make sure that I was on the correct page. And let me move this real quick. Just give you an idea. You see where we're starting at? Whoa! Let's try this again. We are starting in this general area. This is on the rear of the baseband assembly. In other words, you are putting a multiplexer aggregate signal in there, or mission bit stream. In this case, it says transmit mission traffic. It is a connector on it. It'll say data. There's 2 places that it will have if you're doing fiber optics. There are a couple cables that BNC cables that are on the back of it, and this particular one, since we're just going with the data circuit itself, is a rather, I think it's like a 30 or 40 pin connector that has a Loctite on it. It's probably about that big, that gets onto the back of the baseband. But when we tie it in here, the first place that we're going to hit is an attenuator. Now this attenuator, there we go. This attenuator has 30 steps. Okay, what does that mean? Well, let's go back up to the baseband assembly. When you are looking at, go ahead. Okay, well, I'm just pointing it out to you on the baseband assembly. This is in the transmitter portion. If you'll take a look at the module next to the meter and look up, there's 2 switches there. You have a 0 to 10 and a 0 to 20. 0 to 20 is on the top part, 0 to 10 is on the bottom part. In order for us to get 30, the top switch has to be on 20 and the bottom switch has to be on 30. If you want 15, you want to switch the top switch to 10, take the bottom switch to 5. That's how you get 15. The other part of this, the reason why, is we want 3 volts peak to peak, and that's to drive the modulation on this signal at an even rate. The Tisser likes 3 volts peak to peak. It does not like the 5 volts peak to peak, which is probably what the multiplexer is putting out. So we use that attenuator to bring it down. And also, if you have a multiplexer, let's say a couple 100 feet away, it's probably going to be weaker, so you're not going to have to do as much attenuation. But if it's got a short cable to it, let's say maybe 10 feet, you're going to need to use the attenuator because it'll be saturating the front end here, or the back end of the Tisser here. So next up, we have something called a baseband filter. This baseband filter is a notch filter, and it's going to take out the 8.5 megahertz. Now, if you hadn't noticed this transmit mission traffic, it's going to be either CDI or NRZ, and I think the first one, the CDI, is like 72 meg to 72K to 4.608 megahertz, and then if you have pseudo NRZ, it's the fiber optics, which is 6.44 megabits. So you can see that we're not going to interfere with our baseband when we have this notch tuned to 8.5. When we get to the summing buffer amplifier, however, we're going to be combining the Orderwire signal at 8.5 megahertz. Now you see why we cleaned it off at the earlier. That's to make sure that we didn't get any noise that might have been generated by the baseband traffic. So when we put it on there, it's going to be an FM signal at excuse me, at 8.5 megahertz. Excuse me. If you look closely to the right hand side of that summing buffer amplifier in the same LRU, you will see a transmitter subcarrier generator at 8.5 megahertz. That's the reason why. Also, I just want to point out, you'll see the dotted lines around this whole box area. Bottom right hand side of that box, it says the 1A2 A4 transmitter baseband LRU. See how to identify LRUs? So next up, we're going to go through a diplexer. Now, the way the diplexer works, and I showed you an example of one in the earlier slides, is made up of bandpass and low-pass filters. And what this does, if you take a look at that bandpass or the diplexer itself, you'll notice that it will not let the 70 megahertz, which is a receive IF, come in on the same line as our baseband and our Orderwire. And our baseband and Orderwire is not getting onto the 70 megahertz line. When it goes out the rear of the baseband assembly, you have an aggregate signal, which is the baseband. You have the Orderwire on that signal, but in the same context, you have 70 megahertz going the opposite way. So it is a two-way path on a single cable, and they don't interfere with each other. Think about it, 70 megahertz versus just from 72K to, let's just say 8.5 meg. All right? So it's not going to interfere with it, so you basically have a two-way street here. Goes out of the rear of the baseband assembly on the 1 or 2 foot cable and comes directly into the RF assembly. And the first place we're going to hit is a diplexer. Again, it's a two-way street. It's going to prevent one getting on the line with the other, to keep things separate. In this case, now we want to separate the baseband and the Orderwire off of that line and let the 70 megahertz go somewhere else. We hit I'm going too fast here. The first place, if you follow the bold lines, you're going to hit this triangle. Most of the time that I have seen, actually, I haven't seen it change anything. All triangles to me looks like an amplifier. In this case, you'll see right below it, it says, well, not right below it, but in this particular box, you'll see that the amplifier is going to amplify if we have the 150 foot cable. And you go, well, what happens if we have a 2 foot? Is it going to amplify with that? The best way with that is something called a compression amplifier, and I'm not sure if they taught you that in Dolan Hall. The idea behind what's called a compression amplifier is it will always amplify, but if it reaches a certain level, it will compress the signal to make, oh gee, sounds like AGC, doesn't it? make that output a constant level. So whatever the varying input is, depending on the cable, whether it's a 2-foot or a 150-foot, it's going to compensate for that. The next one we have to be concerned with is a transmitter encoder. Now, I showed you yesterday those thumb wheels on there. Now, this is in the operate position. We're going to generate BCDs from the encoder, that's binary coded decimal, and we're going to let this data switch, because we are in the operate position, let it pass through and hit the phase lock loop box. It's going to tell the phase lock loop box what to do with the frequencies. With that phase lock loop box, you're going to start to see, when we use that bold line up there, it is attached to a voltage controlled oscillator. Now that's basically where your frequency begins, and you have modulation. Oh wow. You modulate it, then you up convert it, and what's the next step? Yeah, you amplify it. See how this is falling into the basic transmit baseband to the dissonant end? So there's your first one. You modulate it. It is an FM signal. You'll notice that is in the 7 gigahertz range. This would be considered your IF in the transmit side. Now, when you get right down to it, it's like 7.2 to 7.625 gigahertz. So that phase lock loop, let me back this up just a little bit. This phase lock loop, you can see that it goes down and then onto the black bold line here up to the VCO. Then it hits, you'll see that it goes in 2 places. One goes to the multiplier, the other one goes to the divider. The divider is going to come back down back into the phase lock loop box and hit another divider, and then it's going to hit the PLL. Now, the way this works is when we bring our baseband on the same signal as a phase lock loop, it's going to be separate. Why? Because it's a voltage that the phase lock loop is sensing to produce, to give to the VCO to tell it what to do. The VCO is the actual oscillator, but it sends a sample of the signal to the dividers, and there is a logical mathematical equation. Realistically, it changes it into digital signals, and it counts the pulses. And when it gets to the phase lock loop compares that signal with what the encoder is telling it what to do. And if it needs to make that voltage controlled oscillator either go up or go down, it's going to send out either a positive voltage or a negative voltage to keep the voltage oscillator within that frequency. So when we hit the multiplier, it says ×2. Well, wait a minute, you just told us that that triangle is a amplifier. Oh yeah, it's an amplifier, but the way it makes the frequency is it doesn't have a calculator and takes its ×2. No, it takes the first order harmonic, which is a 7.2 to the 7.625, and makes a second harmonic, a third harmonic, a fourth harmonic, because it's easy to do with FM. So that second harmonic's actually the operating frequency. So that's the reason why it's called a multiplier at ×2. So it amplifies it enough to where it can see the second harmonic, and then it hits this bandpass filter. Well, the bandpass filter is centered between the 14.4 to 15.25. And we're going to weed out all the other frequencies. Oh gee, so now we've gone from modulate to IF to RF. Our next step is to amplify. So when we amplify this, we're running to a field effect transistor. That's what FET means. With the FET, it is a very powerful amplifier, And with that particular amplifier, you're going to get it up to the operating frequency with the power it needs. In other words, wattage. The problem with power amplifiers, when you're amplifying at that high end of the scenario, you will generate a lot of harmonics. When you hit the isolator, we're going to prevent the viswire from getting back into the whole transmit section, because the last thing you want to do is put reflected power back into that FET. It'll smoke it quickly. So we're going to keep the signal separate from the rest. We're going to hit a harmonic filter. Remember, I told you that FM generates a lot of harmonics when it is amplified. With the harmonic filter, it senses anything above the top end of the frequency spectrum for the operating frequency. In other words, about, what is it, 15.25. Anything above that, it starts filtering it out. Because the second harmonic of 15, just an approximate value, 15 gigahertz would be 30 gigahertz. So that's pretty easy to filter out. Then we're going to go through a circulator. In this case, it's pretty easy to understand where it's going to go. It only has one place to go. Why? If you take a look at that switch in the next segment, there's only one way it can go. And if you follow the line that goes up, you'll notice that that goes all the way to another section, and it's not in line. So there's only one path that this can go. So the circulator is going to know what to do, and it's going to hit this switch. Why? Because we have it in operate, and we want it to go out the antenna. Again, that's at standby operate. It's going to control that switch as well as the one above it. Now, when you hit the duplexing circuit, this is where we're going to send it out the antenna. The chances of it getting back on the receive side is slim, very slim. I'm not going to say, you know, it won't happen. It's going to be very slim. And then out to the tisser, out the antenna. So we've gone over transmit path. I've shown you the part where the branch assembly starts to come into play. We went through the basic objective of transmitting baseband to the distant end by, you know, modulation to IF to RF, which is up conversion, and RF amplification, and then we hit where it starts at that isolator from all the way out. That is your branch assembly on the transmit side. Is there any questions on the transmit? Remember, you can ask me later, so, you know, formulate your questions and send them to me. If there are no questions, let's go to the transmit receive side. Again, that we're going to receive it from the tisser, and it's going to project it into the RF assembly through the waveguide, and we're going to hit the diplexing circuit. Again, it's going to keep things separate from the receive versus transmit. First place we're going to go to is that switch. We already know that it's in operate, so it's going to hit the receive line. First place we're going to do is the receive filter. Remember that adjustable filter on the bottom left hand side of the baseband assembly? That is that piece of item right there. You're going to adjust that to the receive frequency. If you didn't adjust it to the receive frequency when you put it in operate, you're probably going to have some issues. Probably won't be able to receive them at all. They'll be able to hear you, but you couldn't hear them if you did not adjust the pre-selector filter. So this one is just tuned where it weeds out most of the frequencies. You hit an isolator. Why? Because you don't want anything coming out of that low noise converter. Oh gee, we hit an amplifier. The low noise amplifier, the whole idea behind this is to amplify a very weak signal, because it probably is going to be very weak. The part is, let me stop myself there. From the isolator all the way out to the antenna, that is the branch assembly. So we've gone through the branch assembly. Now we're into the active components, which we're hitting the low noise amplifier. This is the first stage of the objective, which is recover the baseband. So we're going to have amplification, bring our signal up to where we can get it into this image reject mixer. So let's go back to Dolan Hall basics here and ask you guys, well, what does a mixer do in receive? Let's see if Airman Roundsley can answer that question. No. Okay, do you know what the word is called when you mix those two together? I couldn't hear you. Nope. Modulation is a transmit term. That would be down in the... Go ahead. Anybody? Negative? Okay. Does anybody remember the word heterodyning? Okay. Heterodyne is a receive term. Modulation is a transmit term. And when you say words like, hey, in modulation, that's a transmit clue. When I say heterodyne, it's a receive clue. See how this all plays out? So if you're taking a test and you see, hey, if I want to get the 70 megahertz IF, I need to understand that is a receive function. See how this all, the clues that it gives you? So the reason why I insert this word of heterodyning in here is to give you guys the basic idea that, hey, I did learn something back in Dolan Hall. And what is the combination of two different frequencies? What should I get out? Let's see if Airman Hall knows this one. Negative. You're thinking modems. Okay, I'm in a different realm where it's called radio. How about Airman Green? Do you know? Well, that would be one of the ones that we want. Can you think of any others? Ah, yes, going back to basic electronics. All right, so let me help you out. When you have a mixer like that, and it's in receive, you have the operating frequency, and then you have the local oscillator frequency. Now, those two frequencies must be different. In our case, when we're generating it from the receiving encoder, we're telling the phase lock loop, hey, I need it to be at this particular frequency, telling the VCO what to do, the ×2 multiplier, and then the bandpass. So the idea here is my local oscillator will be 70 megahertz difference from the operating frequency. Why? So I can get the two originals, which would be the local oscillator and the operating frequency, and I'm going to get the sum, and I'm going to get the difference. The difference is the one that we want to focus on, which is the 70 megahertz. So coming out of that mixer, we're going to have four signals. We're going to go to the amplifier and gradually bring these up, because anytime you manipulate the signal like we just did, we're going to need to amplify it. That's a preamp. We get into another amplifier and we see that it's going to generate more power to it. Why? Because we're going to manipulate it again, In this case, the bandpass filter, now this is straight out of the tech order, says that it is centered on 70 megahertz plus or minus 10 megahertz. So the band width or band pass of that filter is from 60 to 80 megahertz, and it passes the difference. And it takes out the sum, it takes out the two originals, and pretty much this is where your 70 megahertz is finally filtered to where you can do something with it. So when you take a look at the microwave LRU, everybody see the microwave LRU? Anybody not see the microwave LRU? Better known as the 1A1, A2. Anybody need help with it? Guess not. So with the microwave LRU, produces the 70 megahertz in receive. Where do we get the final result of the 70 megahertz? When it gets past the bandpass filter. Now you remember when I told you that anytime we manipulate the signal like we just did, we're going to amplify it. And here comes your Agc amplifier. Now this one's going to make sure that whatever the signal is, if it came in too strong, if it came in too weak, it's either going to amplify. It is basically a compression amplifier again. Now this is going to give us enough oomph to get it out of the RF assembly, and it's going to run through the Diplexer again, going to keep that 70 megahertz onto the 2-foot cable and keep the baseband and Orderwire off of the 70 megahertz line or receive path. We go out of the RF assembly into the baseband assembly. Have I lost anybody yet? It's pretty straightforward. Just follow the bold lines. And remember, this is on page 4 and 5. And you'll notice at the bottom of those pages it says transmit baseband, and it'll say transmit RF. So that's for the baseband module or assembly and the RF assembly. In this case, pages 7 and 8 are the receive side of the house, and that's what we're in now. So that would be page 7, and this should be page 8. We look at the receive signal path, page 8 there. We're going to be into the Diplexer. Once we get into the Diplexer, okay. When was that? 9:32. Okay, I'll wait on Javier. Is there any questions while we're waiting on him? Okay, you're back? All right. Did you miss anything there, sir? All right. Must be the speakers on your computer. So when we get into the receive path, the first place we get to is the Diplexer. Again, it's going to keep things separate from getting onto the receive section. When you look at your baseband and Orderwire, and your 70 megahertz is going to be going through. It's the whole idea behind those. First place we're going to hit is the cable AGC, not to be confused with the IF AGC. IF is in the receive section on the other page in the RF assembly. Has everything to do with the receive signal level of the RF that is coming on the front end. This one is going to compensate if we have the long 150-foot cable. Again, it's going to amplify, but if it has the short cable, there may be some compression in it. If you have the 150-foot, more than likely it's going to amplify. We're going to run into something called an Ifd Modulator. This is when we are breaking the signal down from the 70 megahertz, and we now have the Orderwire at 8.5, and we have the aggregate signal, which is either CDI or NRZ. We run through an amplifier because we just manipulated the signal, but now we're going to choose this particular path because I need the baseband aggregate to go through and block the 8.5 megahertz order wire. Well, this low pass filter says it passes mission traffic, but there's a small problem with filters. It's called a roll-off. In our case, the roll-off, there is a small chance that it is not going to block all of the 8.5 megahertz. What does? The notch filter. This one is going to block the 8.5 megahertz. The filter is just in case we generate harmonics back in that amplifier after we have demodulated it. So it's only going to pass the mission traffic, it's going to block the 8.5. This FO and GM interface, that's on the front panel of our baseband assembly. FO meaning fiber optic, GM meaning group modem. You'll notice the group modem passes CDI, fiber optic, NRZ. That's pseudo NRZ. We're going to go through an attenuator, the difference between the receive attenuator and the transmit attenuator. Transmit has 30 dB of attenuation. This one only has 10. Because you've received the signal, and depending on your amplifiers, it will determine what that signal is going to look like going to the multiplexer. The idea is to get it at 3 volts peak to peak. Now, when you have the multiplexer, it's going to sense that it may not be 3 volts peak to peak, and it will boost it up to its 5 volt peak to peak. So again, this is where it is still in the baseband assembly and then out. Now let me get back to an area where I can see it. This is in the receiver baseband LRU, the 1A, 2A, 3. You can see the dotted lines around this whole assembly, or the whole card itself. So that's how you identify it. Any questions on receive? If there is no questions, let's go to Orderwire. Let me blow this box up real quick. I'll show you something on it. You see where the receiver baseband card is? Well, on it you have 2 switches. At the top you'll see GM and FO. This is to switch between the group modem or fiber optics. Again, those are 2 different cables. One has a Canon plug. The other one is 2 BNC connectors on the rear of the baseband assembly. Below it is the attenuator. 0 to 10, only 1 switch. So let's get right into Orderwire. And what you can see is just follow the bold lines. You'll notice that, and I'm going to point to it, I don't have the, for some reason my mouse is not showing up. On the Orderwire LRU, the 1A2, A2, far right you can see that there's a speaker and a connector. On that connector is where you're going to connect your handset, not headset, handset. The input, if you're transmitting, goes through your speaker, goes through the Orderwire intercom connector, goes through the bottom bold line there and hits the transmitter subcarrier generator. This is where modulation takes place for your analog or digital Orderwire. It goes into that 8.5 megahertz, and coming out of it is 8.5 FM Orderwire. And of course it's going to go through and get transmitted out if need to be, or in our case we're going to talk about loopback here real soon. If we are receiving Orderwire, it's going to come on the top part, and like we just went through, it's going to hit the cable AGC, the Ifd modulator, and you'll notice that the low pass filter and subcarrier notch, the subcarrier notch is going to take out the 8.5, so it can't get on that line. But if you look at the bold line, you'll see a receiver, subcarrier, demodulator. Basically, anything that has to do with FM, they're called discriminators. It's either going to modulate or demodulate. In this case, we're demodulate, taking it out, run it through the Orderwire, and then you'll be able to hear it on your handset. Which brings me to that big bold box where that speaker is, where it says Orderwire Intercom switch. This particular switch, if you are in Orderwire, that means you can talk to the distant end. The distant end, and if you have your handset and handset connected to your baseband assembly, headset connected to your RF assembly, you'll be able to talk to each other, and you'll be able to talk to the distant end. If you have it in intercom and in operate, you can only talk to each other between the baseband assembly and the RF assembly. You can't talk to the distant end. So you got to pay attention to where that switch is when you go to operate. Because I've seen students that when they are doing their check and they get, they're transmitting, they forget to take it out. And there is a line in the tech order that says, hey, make sure that you change it from intercom to Orderwire. But some do not get that line, or they'll skip that line, and they'll have it in intercom, and they're scratching their heads why they can't talk to them down there, and vice versa. So just letting you know, that's a tidbit. So what does the Orderwire signal flow do? Well, there you go. You can look at the sentences there, routes the signal, transmit baseband, and make sure that you got to be in the Orderwire position in order to talk to the distant end. Here's your transmitter subcarrier. This is going to modulate it. And when you get through the demodulator in, it's going to get back into your analog where you can hear it on your handset. You got a test tone oscillator that's in there. Word of caution, when you're doing your labs, do not have the headset on when you do test tone. You do not want to be deaf coming back here. I've seen many a student, no matter how many times I tell them, hey, don't put the headset on anytime soon until you're doing a intercom and Orderwire check between each other. You put it on test tone, that 2.6 kHz has no volume control in your ears, and it is loud. So just a word of caution, please. Keep the headset and the handset on top of everything when you're doing test tone. You might just have to pick it up just a little bit just to listen in on the headset, and same with the handset. So it's just a precautionary measure. Comes with a caution, does not come with a warning unless you keep the headset on for very long. You got a test tone detector. This is on the front panel. Those are the lights that's on there. Let me see if I can, there we go. Blow this up for you. You can see anything that says T/T, that's your test tone light, and that's if you have it in the test tone position. The test tone switch is right above the standby operator on the far left there. So just to give you an idea where these lights are. Next up, we have something called standby loopback, and we're going to focus in on the RF assembly with that. You'll notice that there's a lot of bold lines compared to the transmit and receive on this. The one thing that's not highlighted on your transmit side is a transmitter encoder. And you're going, okay, I give up. Why? Well, remember I told you that we have frequency diversity, and we use the frequency transmit that is 200 megahertz off of the receive frequency? Well, that's frequency diversity. So that way, when I'm in transmit, I don't interfere with the receive side, and when I'm receiving, I don't interfere with the transmit side. So with this transmitter encoder, it is controlled by the data switch. Data switch is right next to it, and then I'm talking about the transmit synthesizer LRU, the 1A1, A4. If you look above the 1A1, A4 synthesizer LRU, past the logic, there's a transmit encoder. You'll see the data switch is highlighted. The standby operate switch controls the data switch. Without that control, if you're in operate, it's going to let the transmitter encoder do its thing and transmit out the operating frequency. But like I told you before, they're 200 megahertz apart between transmit and receive. Well, if I'm doing a loopback, it doesn't make any sense for me to use the transmit frequencies because I can't receive them. So how does it do a loopback so you can do all your checks? Well, the data switch now takes the transmit encoder and switches it out for the receive encoder so it can loop the signal back. So it's all on one frequency and you don't have a problem with that. And it does the same thing with the same signal except for going out the antenna. Let's go into the microwave LRU. Right above that, where the microwave LRU is making that statement, the 1A1, A2 section, the bottom right-hand corner of it, if you look right above it, you'll see that the standby operate switch is no longer in the operate position, but in the standby position. Now, when you come out of that harmonic filter, you have approximately 316 milliwatts or 25 dB of gain or 25 dB of signal strength. You don't want this to go right into the receive section. Why? It'll burn it up. So how do we compensate for getting that signal down in strength? Well, you see the dummy load right above the switch there? That's one place it's going to go through. And then when it goes through the top part of the pre-selector filter, it does go through the filter twice. So if you didn't have your pre-selector filter close to the signal, you may not get your loop back. So we take that output frequency, go through the first part of the pre-selector filter, and we hit an attenuator. That attenuator is going to prevent us from overdriving the receive section. And then it loops back through the switch into the pre-selector, and then it's going to make it 70 megahertz. That's where the test tone comes into play, and that's where you, when you speak on the handset and the headset, how you determine if your order wire is working as well as your transmit and receive section in the whole assembly. So by looping it back, you'll be able to check everything out. And that is with the standby operate switch in standby. So let's take a look at what it comes up with. The data switch is the most important part there. It is controlled by the standby operate switch. It is in standby mode. And of course it shows you the relay 2 where instead of going out the antenna, it's going to go through the attenuator and dummy load as well as the filters. There's standby relay 1. So we've gone through the purpose, the operating characteristics, the types of traffic, the equipment, and signal flows. Any questions? Again, this is all out of our tech order, almost word for word when we pull these things out and give you that caption there. Any questions? All right, so let me pull up the last one that we need to do. I do not understand why PowerPoint makes this a problem. Unit 5 alpha. Identify relationships of basic facts and state general principles associated with controls and indicators of the tropospheric satellite support radio system. Wait a minute. Did we go through that on the TO? Yeah, we did. This is just going to highlight some places that we've already gone over. So we just go through the slideshow to show that, hey, you know, this is part of it in what I did yesterday. Just remember, you got to make 70% on the test. That means you got to get 28 of them correct. You can only miss 12. So you're going to be dealing with the TISR starting tomorrow. If I read your labs correctly, I see that you will be done by 12 o'clock with labs, which means that we get to do our homework or go over appraisals tomorrow afternoon. I'm still trying to find out how long this meeting is going to be, whether or not I'm going to be crunched for time. So it may be later in the afternoon instead of earlier because I have another class to teach. So the overview is familiarization of the TISR controls and indicators. There is a lot on the front panel that you're going to be playing with. As you know that we went over page 4-2 and 4-3, table 4-1, as well as 4-2 for the RF assembly and baseband assembly. Any questions? Yeah, that was quick. No questions? Really? All right. So, Senior Airman Alvarez, what are the 3 self-clocking signaling formats? If you're saying something, I can't hear you. I see that your avatar's lit up, but there is nothing there. You can go ahead and put it in chat if you need to. Oh, cheater. How about Airman Green? Do you have an idea? Outstanding. So what makes CDI so much different, Alvarez? How about you, Senior Airman Rapoli? Any idea? What makes CDI so much different than the other signaling formats? Okay, that's the key word there. Transitions. It does not look at voltages. It's more worried about how many transitions are in a clock cycle with the data. All right, pretty good. Javier, you have a question on the 3 steps of PCM. Mm-hmm. 3 steps of PCM. Okay, not in order, but it'll work. Griffin, what is the problem with the second step with quantization? Griffin? Caught you guys off guard. Okay. Go ahead and restate that because both of you kind of trounced each other there, Sergeant Kinnan. Yeah, and what's the error called again? Okay. And Hall looked like he had something to say. Okay. Uniform causes those errors, the rounding errors, but what is it called? Standing? Yeah, quantization errors. Good. Now, I know Price will know this answer. What corrects for most of those quantization errors? Exactly. Non-uniform quantizing. All right. So, you know that I'm going to ask some questions. Here's what I am thinking. At 1 o'clock, hear me out. 1 o'clock, we can go over homework. Correct? Which is from 3 alpha to, I'm thinking 5 alpha. It's been a few days since I last looked at it. It is 5 alpha. Can someone help me out with that one? Okay. Is this enough time to get you through your homework, what you got left at 1 o'clock? Or should it be 2 o'clock? Okay. Okay, let's go with 2. Because I'm trying to get you guys to where you have all your homework done. You can, rest assured that you either got it correct or did not get it correct, and you're going to correct it. And then we're going to go over appraisals Friday, but that is to be determined hopefully by this afternoon. As soon as I find out about our meeting, if I can get out of it or if I'm going to have to adjust. All right. Oh, believe me, I hate meetings with a passion, especially if it's with everybody. Most of the time, the meetings last maybe 15 minutes, but we always get that 1 or 2 people that need to have it re-explained in a different way. It's like, okay, just wait till after meetings to do that. Yeah. Well, we live and learn, right? All right, 2 o'clock this afternoon, we shall meet again and go over from 3 alpha to 5 alpha. Any questions? Okay, we'll see you then. You guys have a wonderful day, and 2 o'clock. All right, take care.